Okay, let me discuss the estimation. The first estimator we usually considered in the textbooks is the indirect least squares. So it is taught in textbooks to give students some intuition, but it is never used in practice. So it is not it's bad. Let me see. Like, for example, think about the identified model in Model 3. Then we learned gamma 1. So you first identify pi 11, pi 12, pi 21, pi 22. So you may you can estimate those four reduced form parameters easily. And then we learned from the identification result that gamma 1, gamma 2, beta 1, beta 2 can be identified by calculating them. So you can just implement this in estimator. So you estimated pi 12, pi 22, then take their ratio, which could be an estimator for gamma 1. So this is the indirect least squares. So it is called indirect because your least squares method is applied to not directly to the structural parameter, but indirectly to the reduced form parameters. So reduced form parameters are estimated by least squares, and they are converted back to structural parameters. Okay, so then the idea is straightforward. So that is why this estimator is considered in the textbooks. However, it is not it does not have it is not desirable. It's not optimal in many cases, especially as you can see, calculating the ratio directly is not a good idea because if the denominator is small, like say if pi 22 is a small number relative to the numerator, then this will can be a huge number by some estimation error. So the estimation error in this kind of nonlinear transformation may be amplified and may not be efficient in the end. So similarly, like for example, think about the IV regression model, standard triangular equations model. You may apply the same indirect least squares there. And some textbooks have this argument in teaching IV regression, but no one uses this method in practice. So you can do the same thing. First, estimate gamma, which is easy. Estimate the first stage equation, and then estimate the reduced form equation of y on z. And then pi can be written in this way. So beta in the end is the ratio, but never use this method in practice. I used a similar intuition when I first teach the identification of IV regression model. So at that time, I considered education and the quarter of birth and wage. So in this example, I used the same idea like this, but it is not used in practice. As I said, the problem is the ratio, it's not efficient. The error there may be a huge error in the result. And then another different thing to think about in the estimation is whether so suppose that there are 10 endogenous variables. So there are 10 equations, but you are interested only in one equation of them. So you are looking at a macro model. Macro model has to consider a lot of variables at the same time. But you are interested only in, say, the financial market or the labor market or a specific market in the macroeconomy. Then you can think about two different approaches. You are interested in that market, then you can simply ignore the other markets and utilize the only market you are interested in. That approach is called limited information approach. You ignore the other markets and you use the information that you need to use. So if they are not required, then you don't need to use. Otherwise, on the other hand, full information approach is literally you estimate all the markets to obtain just one market. So even if you only need one market, still you may estimate the whole market and so just use the part of the results. Both are reasonable approaches, but there are pros and cons, obviously. The main problem here is, so full information approach would be ideal because if it is efficient if all the equations are true. So the problem here, you are when you set up big macroeconomic models, you are imposing a lot of assumptions on different equations. If you believe that all the equations assumptions are true, then utilizing them will be efficient. But the problem is, on the other hand, you are making a lot of assumptions. You are interested in only in the stock market, but you have to make assumptions in the labor market and in like a trade market and like in other markets. So if you use all the information at the same time, if like say labor market assumption is wrong, then its misspecification bias may arise some bias in the financial market, which is a problem. So that's it's the problem. On the other hand, limited information approach is exactly the opposite. You do not care about the other markets. I don't know what assumptions are used there if they are not needed. So you are looking only in one market. So it is robust because you are imposing fewer assumptions. But the problem is it may not be fully efficient. So you are losing some of them. And also, another advantage of using limited variable approach is shown here. In toy model 4a, as you see, I am interested, if you are interested only in here, say you are interested only in gamma 2, then you do not need to estimate this. If you try to estimate this, you can't. You cannot estimate the other equation. So in this case, you have no choice but to use the limited information approach because the other equations are not identified. So this is another way to understand the difference between full information and limited information approach. Was that right? And then finally, but in practice, we are going to use the GMM method. In the earlier examples, I gave you the moment conditions implied by the model. So then you may apply the GMM method in the same way we did in a previous chapter. So the estimation is not much difficult once you set up the moment conditions, and then everything is linear, so it works well. Okay, this is it. This is the end of this chapter, and next chapter will be the last one in this semester. It will be about quantile regression. So I will continue on the next one. See you later. Bye.